My name is Naveed Akhtar and I am going to present our work titled as Repeated Constraint Sparse Coding with Partial Dictionaries for Hyperspectral Unmixing. Remote sensing airborne and spaceborne sensors take hyperspectral images of the Earth's surface for geological studies. These images can be represented as hyperspectral cubes with two spatial and one spectral dimension. For a typical hyperspectral image, the spectral dimension consists of hundreds of contiguous bands in the visible and short infrared wavelength range. However, each pixel of the image cube represents a large area on the Earth's surface in the spatial dimensions. Along the spectral dimension, each pixel of the cube represents a spectral signature of the Earth's surface. Due to low spatial resolution of the sensors, a pixel is usually a mixture of reflectance spectra of different materials on the ground. Each of these spectra is known as an end member, whereas the proportions of the end members in the mixed pixel are known as their fractional abundances. Hyperspectral unmixing is the process of separating a spectra measured at a pixel into its constituent end members and estimating the corresponding fractional abundances. In this work, we formulate hyperspectral unmixing as a constraint sparse approximation problem, and we propose two different methods for hyperspectral unmixing under sparse regression framework. The proposed methods are called repeated constraint sparse coding and repeated spectral derivative. Both of these methods repeatedly solve a sparse approximation problem to achieve their goals. We have evaluated the proposed methods using synthetic hyperspectral image cubes as well as the real hyperspectral data. For the synthetic images, we have created the mixed pixels using the spectral signatures from the US Geological Survey Spectral Library. This is a publicly available library that consists of reflectance spectra of over 1400 materials. The fixed dictionary used in the sparse approximation process is also created from the same library. We have also evaluated the proposed methods using the real hyperspectral image cube that is acquired by NASA's Airborne Visible Infrared Imaging Spectrometer. Again, we use the US Geological Survey library in the sparse approximation process for this image. This figure shows some results on synthetic images. The curves show the mean values of the correctly identified end members as percentages as a function of the signal to noise ratio of the images. The proposed methods, which are shown in red and black, are compared with the state-of-the-art method proposed by researchers at German Aerospace Center, which is shown in magenta. The blue curve shows the results of directly solving the constraint sparse coding problem for hyperspectral unmixing. The proposed methods can be seen to outperform the other methods, especially at low signal-to-noise ratio. The plots in this figure show the fractional abundances of wrongly identified end members as a function of SNR. Again, the proposed methods show good performance at low signal-to-noise ratio. As can be seen, the repeated constraint sparse coding method performs particularly well at low signal-to-noise ratio. For the real data, we chose a hyperspectral image of a geologically well-studied region of the cuprite mines in Nevada. The figure shows the classification map of this region as computed by tetracoder software. Please notice the pattern in the orange color in the image. This pattern corresponds to a mineral that is called alunite. We perform the unmixing of the hyperspectral image of the magnified region using the proposed methods. The figures at the bottom of this slide show the maps of the fractional abundances of alunite in the region as computed by the proposed methods. The figure at the top shows the reference classification map. With a visual inspection, it can be seen that the proposed methods are able to assign high fractional abundances to the regions that are classified as alunite in the reference map. To conclude, in this work, two methods have been proposed for hyperspectral unmixing under sparse approximation framework. Both of the proposed methods have been shown to successfully perform hyperspectral unmixing on synthetic and real data. The method called repeated spectral derivative performs better at high signal-to-noise ratio, whereas the other method, called repeated constraint sparse coding, shows overall robustness against noise. With this, I thank you all for your patience listening.